Hello and welcome to another physics summary video, this time on the high level topic 9.3, which covers Young's double slit, multiple slit, diffraction gratings and thin films. So it's quite a large topic. Just to remind you of the Young's double slit, we have two slits separated by a distance d, little d. We have a distance from the slits to the screen, big D, a fringe spacing of little s and a wavelength of lambda. We can work out the fringe spacing using this equation, lambda big D over little d. If we plot the intensity as a function of angle from the central maximum, what you have to know now for the high level is that the double slit pattern is modulated or enveloped under the single slit pattern. So we no longer have a constant intensity. We have this intensity which decays with the single slit pattern. In the double slit pattern, the number of slits, big N, is equal to 2. However, for multiple slits, we're increasing the number of slits, big N, and as that happens, we get the presence of N minus 2 secondary maxima, these two here. We have more intense primary maxima because intensity is proportional to N squared. So if we had 4 slits, then the intensity relative to one slit would be 16 times as much. And we have thinner primary maxima because the width of the primary maxima is inversely proportional to the number of slits. Now, diffraction gratings are useful when we want to study gases, and we use the so-called diffraction grating equation n lambda equals d sine theta when working with diffraction gratings. If we shine a sodium lamp on a diffraction grating, we'll see the brightest line in the central maximum, that will be straight ahead. Then we have n equals 0. But as we move the observer moves their eye away from the central maxima, the next time we see constructive interference will be when n equals 1. That means we'll have a path difference of 1 wavelength. And the next time we see constructive interference, we'll have a path difference of 2 wavelengths. That will be when n equals 2. To find the distance between the slits, little d, we have to take 1 divided by the number of lines per millimeter, which is what defines diffraction gratings. Then we will get a d in millimeters. And the last concept to talk about for 9.3 is thin film interference. That's when we have a single ray of, in this case, red light going from an air to film air interface. What happens at the surface here is that there's a reflection at A, some of the ray is reflected, and there's a phase shift at the same time. However, some of the wave gets refracted into the film, then it's reflected back off the film air interface, and then refracted back from film to air, and the rays become parallel and meet the observer here. So we can have interference between these two rays because there has been a phase shift. So we have some conditions for interference. If we've had an odd number of phase shifts, i.e. in this case we've had only 1 pi phase shift, the condition for constructive interference is 2dn equals n plus a half lambda, where d is the thickness of the film and n, little n, is the refractive index of the film. However, the condition for destructive interference becomes 2dn equals m lambda. However, if we were to have an even number of phase shifts, for example, if I had an optically more dense medium here below, then the conditions for constructive and destructive interference swap. This phenomenon of thin film interference is the reason why you see colours on the surface of a soap bubble, but also how we can make anti-reflection coatings on, for example, glasses.